Hey guys, we're going to be looking at a way to solve counting problems using recurrence, motivating it with the Euclid 2019 question 9a. The question starts with looking at a 10-letter words made up of just A's and B's. How many of them do not contain the sequence ABBA? Well, you might go case by case, but you run the risk of double counting, and in this case triple counting, and all in all it's a big mess that doesn't scale. Instead, we're going to be using a more robust method using recurrence, which lets us build bigger sequences from smaller sequences. First, let's think about tracking how close a word is to forming ABBA. We define 4 states. State 0 means no letters of ABBA have been matched so far. That means the letter at the end is just a B. State 1 means we matched an A at the end. State 2 means we have an AB. And state 3 means ABB. By keeping track of these states as we add letters, we can avoid counting words that would complete the forbidden pattern. Notice how each state transitions when we add either A or B. This setup is key for building our recurrence. Now let's write equations for each state. Record the number of valid words of length n ending in state I as f sub n of I. Basically, these equations on the screen just represent how we can get from one state to another state, how many ways we can do that. For example, take the first one, f sub n of state 0 equals f sub n minus 1 of 0 plus f sub n minus 1 of 3. Because a word in state 0 can either stay in state 0 or come from state 3 without completing ABBA. A state 0 means 3 B's in a row. Why is that? Because if there's only 2 B's and an A at the end, then that means it's in state 3 because the end of this sequence is ABB. State 0 essentially means that we have not matched ABBA at all in our ending sequence. Now, using this kind of thinking, we can find all of the other relationships between the states. For example, the last one, f sub n of 3, is equal to f sub n minus 1 of state 2. That's because the only way to get to state 3 is from state 2. These equations tell us the number of valid sequences in each state, how it grows as we add letters. Next, we want the total number of valid words of length n, which we'll call uppercase F of n. That's just the sum of all the states. So uppercase F of n equals F sub n of state 0 all the way to state 3. Substituting the state equations gives a long expression, but we can simplify it. We see that some F terms appear more than once, so we can combine them. After combining terms, we get the equation on the screen. This shows that each state contributes in a predictable way. Using this, we can go from f of 1 by just like reasoning, it can be either A or B, and then we can build this up all the way to f of 10 equals 631. So what did we just do? We started by breaking the problem into smaller pieces, states. Then we wrote rules for how sequences can grow without forming ABBA. By combining these rules, we got a single recurrence formula that lets us compute uppercase F of n quickly. This method shows the power of recurrences. Local rules about the ends of words leads directly to a global count. Remember, the key idea is when only the recent letters matter, counting sequences naturally leads to a recurrence formula. I hope you learned something today and subscribe for more content.